Hello and welcome back. For this video, we'll be discussing geometric sequences and how they're related to exponential functions. If you take a look at our goals here, we want to identify and generate geometric sequences. We want to construct and use exponential functions for geometric sequences. That's where they're related. And of course, we've got our vocabulary here, geometric sequence, and what is a common ratio. So for our first vocabulary word, geometric sequence, it's a pattern of numbers that begins with a non-zero term, and then each term after is found by multiplying the previous term by a non-zero constant r. And a common ratio is just that non-zero constant value that we're multiplying by the previous term. So the biggest difference between geometric sequences versus arithmetic sequences is a geometric sequence has a common ratio, and an arithmetic sequence has a common difference. So how do we determine if a sequence is geometric? Okay, so we've got our first term, our second, third, and fourth term, and then we've got a sequence after that. And the way we can determine the sequence is we take any number, let's say the 144, and we divide it by the number right before it, as we did over here, and you see it's a negative 1/3. And if we take the negative 48 and divide it by the number before it, same thing happens again. We get negative 1/3. So 16 divided by negative 48 will give us a negative 1/3. Since the ratio is the same for all the terms, which was 1/3, the sequence is geometric, because going forward we're timesing by 1/3, negative 1/3. So times by negative 1/3 times again by negative 1/3. All right, so now we need to determine if the sequence is geometric and then explain why or why not. Okay, so if we take this first one and divide by 16, so 12 over 16, that gives us 3/4. Then we'll take the 8 and divide it by 12, and that gives us 2/3. And 4 divided by 8 is going to give us 1/2. Now, since the ratios right here are not the same, the sequence is not geometric. In fact, we could take it a step further and subtract here. So this is actually a -4, a -4, and a -4. Since I'm subtracting the same amount each time, this sequence is actually arithmetic, not geometric. All right, so we want to determine whether the sequence is geometric. If so, determine its common ratio, so the number we're multiplying each time. So if I take 20 and I divide it by the previous number, I get 2.5, so I'm multiplying by 2.5 there. And the 50 divided by 20, I get 2.5 multiplication, and divided by that one, I get 2.5. So the sequence is a geometric sequence. It has a common ratio of 2.5. So if I wanted to find the next number above 125, I simply take the 125 and multiply it by 2.5, and that will give me the next term in the sequence. Take a look at part B. Even though it doesn't have the ones on the top, I can still put a 1, 2, 3, and a 4. So take this 0.07 and divide it by negative 0.7, and we get negative 0.1. And then the 0.007 negative divided by 0.07, and we get negative 0.1 again. And one more division here, and you'll see we get negative 0.1. Okay, so the sequence is, so we're going to write is here, a geometric sequence. It has a common ratio of what we got here, which is negative, and I'm going to put a 0 in there, negative 0.1. All right, now they want us to find terms of a sequence, so we want to find the next 3 terms. So I have term 1, 2, 3, 4, so they're asking us to find terms 5, 6, and 7. So what are my missing terms of the sequence? Well, if it's geometric, we've got to first figure out what the geometric common ratio is. So 16 divided by 64 appears to be 1/4. I'm going to check that one more time. So 4 divided by 16 is 1/4. So my common ratio is 1/4. So to find the next term after the 4, to go to 1 to 5, I'm going to take 1 and times it by 1/4. And we end up getting term 5 as 1/4. So I'm going to put term 5 over here. Underneath it, I'm going to write 1/4. And then term 6, whatever that is, and then term 7. Okay, so how do I find term 6? Well, I take term 5, which is 1/4, and times it by the common ratio of 1/4, and we end up getting 1/16. Then how do we find term 7? There should be a 7. We take the previous term, which is 1/16, and times it by the common ratio of 1/4. We end up with 1/64. I'm going to do the same thing for part B. So I'm finding terms 5. Let me extend this out. 6, and 7. Okay, so 8 divided by 12 appears to be 1.5, and 18 divided by 12 is 1.5. So we'll do it one more time just to make sure. So 27 divided by 18 is 1.5. So my common ratio, my R value here is 1.5. So how do I find term number 5? Well, go back to term number 4, which is 27, and times it by 1.5. And the fifth term ends up being 40.5. Then we take this term and times it by 1.5. To get the sixth term, that would give us 60.75. And then times by 1.5, and that would give us 91.125. All right, so we got a geometric sequence, and how are they related to exponential functions? Okay, so the nth term, which is a sub n, of a geometric sequence, with the first term being a sub 1, so the 1 here stands for first term in the sequence, and a common ratio of r is given by the following formula, where n is any positive integer, a sub 1, but also r cannot equal 0, so you don't want a base value of 0. So you'll notice this looks a lot like exponential. Exponential looks like this, y equals a times b to the x power. But the only real difference here is we're subtracting 1, whereas over here we were not subtracting 1. That's because sequences start with term number 1, then they go to term number 2 and term number 3. They do not start with term 0 and then go to term 1 and term 2. By the way, term 0 would be the y-intercept of a graph. So these are just offset by one term over. That's why we have the -1. So it's the first term in the sequence, the nth term minus 1 to offset by the first term. And that's the only difference in these two formulas. Okay, for our next example, finding the nth term of a geometric sequence, use an explicit formula, which we have over here, to find the 11th term. So the nth term in this context is 11. So the 11th term, if you look up here, I have 1, 2, 3, 4, but I want the 11th term. So rather than going through the 5th, the 6th, the 7th, the 8th, and so on, we can actually use this formula over here, the explicit formula, to figure this out. So a couple things we need is the first term, a sub 1, which is going to equal the 512. Then we need to figure out the common ratio. So what's the common ratio going to be? So remember, the common ratio is found by taking any term in the sequence and dividing it by the one before it. So 256 divided by 512 leaves you with 1/2. I'm going to check that one more time. So 128 divided by 256, and that leaves you with 1/2 also. So my common ratio is 1/2. Now to find the 11th term. So n is going to equal, nth term is going to equal 11. So I'm going to find a sub 11. So the 11th term is going to equal the first term, which we said was 512, that's over here, 512, times, and then the r value is 1/2, 1/2, that's what we get from here, raised to the n minus 1, so it's 11 minus 1, so this exponent's actually just going to be 10. Simplify this a little bit, so the 11th term is going to be 512 times, now 1/2 to the 10th power is going to give us 1 over 1024, and then we'll simplify that a little bit further, and the 11th term ends up equaling, when we do 512 times 1 over 1024, we end up with 1/2. So if we extend this all the way out to the 11th term would be 1/2. Okay, so now they want us to use a geometric sequence. So North Dakota's population is increasing more quickly than any other states. In 2011, the population was this amount, so that sounds like the first amount. A sub 1, the first term in the sequence, would be 68,542, has been increasing by an average rate of 2.5% a year. So that would be your rate plus 2.5%, 2.5%, but remember, percents have to be in decimal form. So it's going to be 1. That should be a 1, by the way. 1 plus 0.025, which will give us a rate of 1.025. So that's our R value. And they're asking us to find, if this trend continues, determine the estimated population in 2030. So the number of years from 2011 to 2030 would be 20 years. So they're asking us to find the 20th term in the sequence. So a sub 20 is going to equal the first term, which is 685,242, times the common ratio of 1.025. That stuff comes from here and here. Raised to the 20 minus 1 power. We'll simplify that a little bit. 685,242 times 1.025 to the 19th power is what we're really looking for. Now make sure you use a calculator for this. Do the exponent first, and then times that by this number. And the 20th term is approximately equal to, now remember the 20th term is representing 2030, is approximately equal to 1,095,462.